Okay, it's been 5 minutes. I will get started. Homework number 9, the last homework will be due on the 3rd. The review of chapters 10, 11, and 13, which is what the final test will be on the 8th, and the test will be on the 10th, which is our last day of class. Yes. I was about to get to that. Yes. So I have your graded exams up here. In general, you did quite well. Made it easy to grade. Thank you. And the grades are also up on Blackboard. We will not be having a lab today because I decided that I'd like to finish off chapter 11 before the last lab, and just, it's been a really busy week. Chaotic week. So we'll have our last lab next week. If you have any labs you need to make up, you can come in on Wednesdays earlier in the day, or just other days earlier in the day, but Wednesdays would be particularly good because I'm doing makeups in another class that day for labs, so I'll be ready to do makeup labs with people. Or just let me know. Yeah, so let's finish off chapter 10 and start chapter 11. So in chapter 10, we were dealing where we got to on Monday. We were talking about conservation of energy. So rotation adds an extra kinetic energy. So like with our potential energy, we had potential energy from springs and potential energy from gravity. We now have kinetic energy from translation and kinetic energy from rotation. One of the useful things we can do is if we plug in, we use our relationships for that. You've used the relationship that, you know, velocity is equal to omega times radius. So omega is equal to velocity over radius. We can, for something that's rolling without slipping, we can plug that into this equation. And we get this relationship that we have, the total kinetic energy is 1/2 mass times velocity squared times 1 plus I over mr squared. So that's our total kinetic energy. And this factor is sort of the multiplier you get that depends on the moment of inertia of the rolling object. So the kinetic energy of a rolling object is a multiple of the kinetic energy of translation. Basically, you need extra energy to spin the thing. And it depends on what the moment of inertia is. So if the moment of inertia is really big, it takes a lot more, but if the moment of inertia is small, it takes less. So here we have two objects that are the same mass and the same radius, are released simultaneously as they roll down a slope. The disk will reach the bottom first because its moment of inertia is smaller than the moment of inertia of the hoop. So as it rolls down, more of its energy, more of its gravitational energy becomes translational kinetic energy and less goes into rotational. Dante? So more of it becomes translational and less is rotational. And so as the energy, so in general, as potential energy is converted into kinetic energy, because more of that potential energy is converted into translational energy, this disk will roll faster than the hoop. So here's a problem about this. I just answered this, but If a disk and hoop of the same mass and radius are released at the same time at the top of an inclined plane, does the disk reach the bottom of the plane before, after, or at the same time as the hoop? Well, I literally just went through the logic for this. So kinetic energy is translational kinetic energy plus rotational kinetic energy. So 1/2 mv squared plus 1/2 I omega squared. That equals potential energy. We want to figure out which of these, the moment of inertia of a disk is 1/2 mr squared. The moment of inertia of a hoop is mr squared. And because of this, I for the disk will be bigger, will be smaller than I for the hoop. So more energy will go into translational kinetic energy than rotational. And thus, the disk will roll faster. It will have a higher velocity than the hoop. You can think of it as that we have, oops, because K is equal to 1/2 mv squared times 1 plus I over m r squared. And so here we have basically we have mgh equals 1/2 mv squared 1 plus I over mr squared. So for the disk, for some height, just sort of, we want to figure out velocity. We get velocity squared is going to be gh over 1 plus I over mr squared. Sorry, 2gh. So velocity of the disk squared is 2gh over 1 plus 1/2 mr squared over mr squared, which is 2 over 1.5 times gh, while velocity squared of the hoop is 2gh over 1 plus mr squared over mr squared. So that's just gh. 2 over 1.5 is 4/3. So this is like 1.33 gh, and this is just gh. Or d, sorry, delta h. But so for at any height, the disk will be going faster than the hoop, so it will reach the bottom first. Any questions about that? Okay. So here we have a ball is released on a no-slip surface from rest, as shown, and it will roll without slipping down this half of the curve. Then when it begins to rise again, it's on a frictionless surface. When the ball reaches its maximum height on the frictionless surface, is it at a greater height, a lesser height, or the same height as when it was released? I will let you think about that for a few minutes. So, who thinks it's going to end up at a greater height than when we started? Who thinks it'll end up at the same height that we started? Who thinks it'll be lower than we started? Well, those who guess lower are correct. So what happens here is less height because some of the energy from rolling down the hill is in rotation. But when it's on the frictionless surface, it can't get that energy back out. So it will keep spinning, and some of the energy that it got starting here will be in spinning, and it won't get as high up the slope. Because it will just convert the translational kinetic energy it had, which is not all the energy it had potentially at first, and it will still have rotational kinetic energy, and so it will be at a lower height. Here we have a block connected to a pulley. A block of mass m is attached to a string that's wrapped around the circumference of a wheel of radius r and moment of inertia I. The wheel rotates freely about its axis, and the string wraps around its circumference without slipping. Initially, the wheel rotates with an angular speed omega, causing the block to rise with linear speed v. To what height does the block rise before coming to rest? Give a symbolic answer. So this whole thing starts with a mass at height 0, but everything is moving. So the mass is moving upwards with some velocity v, and the wheel is spinning with some angular speed omega. And eventually it comes to rest. The mass has 0 speed, the wheel is no longer spinning. So what is the height that it comes to rest at? So this is a conservation of energy problem. You have two sources of energy. You have the energy of the kinetic energy of the block and the kinetic energy of the wheel. So our final potential energy is equal to our initial kinetic energy. So mgh equals kinetic energy of the mass plus kinetic energy of the point. So 1/2 mv squared plus 1/2 I omega squared. But we can simplify this a little. We can relate omega to velocity. Well, our height is going to be 1/2 mv squared plus 1/2 I omega squared over mg. So there's two ways we can write this out. We can write it in terms of omega or in terms of v. So height is either 1/2 m omega r squared plus 1/2 I omega squared over mg, or 1/2 mv squared times 1/2 I v over r quantity squared times mg, which you could, if we do it in terms of v, we can combine some terms and we'll get, with a little bit of this, we get v squared over v squared over 2g times 1 plus I over mr squared. So that's what you can get with a little bit of manipulation. V squared over 2g equals 1 over 1 plus I over mr squared. Any questions? Nope. Okay. So here we have a problem with an actual numbers. Yo-yo man releases a yo-yo from rest and allows it to drop as it keeps the top end of the string stationary. The mass of the yo-yo is 0.59 kilograms. Its moment of inertia is 2.5 times 10 to the minus 5 kilogram meters squared. And the radius of the axle the string wraps around is 0.0068 meters. What is the linear speed of the yo-yo after it is dropped through a height of 0.5 meters? So again, this is another conservation of energy problem. So if we go through some of the things we know, mass is 0.059. I'll work these out. Well, I might have just screwed up the mass is 0.059 kilograms. Moment of inertia is 2.5 times 10 to the minus 5 kilogram meters squared. Radius is 0.00068 meters, and height is 0.5 meters. And we are looking for final velocity. So our initial potential energy equals final kinetic energy. So mgh equals 1/2 mv squared plus 1/2 I omega squared. And we can replace omega with V over R. And do a little bit of pull out the V squared, 1/2 m squared plus 1/2 I over R squared. I could have done this better. So V squared equals mgh over 1/2 mass plus 1/2 I over R squared. And then I plug the numbers in. There's a better way you could have solved this. You could have done mgh equals 1/2 mv squared times 1 plus I over mr squared, and then V squared is 2gh over 1 plus I over mr squared. And then you have mass in fewer places. But this will get you the same thing. 0.059 kilograms times 9.8 meters per second squared times 0.5 meters over 1/2 times 0.59 kilograms plus 1/2 times 2.5 times 10 to the minus 5 kilogram meters squared over 0.068 meters squared. Which is V squared ends up being 0.964 meters squared over second squared. So V is 0.982 meters per second. And I did put these in, I just screwed up the order of the animations. 0.059 kilograms, I equals 2.5 times 10 to the minus 5 kilogram meters squared, R equals 0.0068 meters, H equals 0.5 meters, and V0 equals 0. And V final equals question mark. And that, any questions about this, is the end of chapter 10. So in summary, describing rotational motion requires analogs to position, velocity, and acceleration. Theta in radians is arc length over radius, S over R. Average and instantaneous angular velocity, average angular velocity is delta omega over delta t. Instantaneous is d omega dt. Average and instantaneous angular acceleration, alpha average is delta omega over delta t. Alpha is d omega dt. Just like regular acceleration and velocity linearly. Period. Time for one complete rotation is 2 pi over omega. Counterclockwise rotations are positive. Clockwise rotations are negative. the linear and angular quantities correspond to each other. X corresponds to theta, V corresponds to omega, A for acceleration corresponds to alpha. Here are the equivalent linear and angular equations of motion where you just make substitutions. You know, V equals V naught plus AT, omega equals omega naught plus alpha T. You know, X equals X naught plus V naught, T equals 1/2 AT squared, theta equals theta naught plus omega naught T plus 1/2 alpha T squared, and so on. To connect tangential speed and angular speed, tangential speed is radius times angular speed. Centripetal acceleration is radius times angular speed squared, so r omega squared. It's also equal to tangential speed squared over radius. Tangential acceleration is radius times alpha. These are at right angles to each other, so if you want to figure out the total acceleration, you can use the Pythagorean theorem. For rolling motion, omega equals V over r. The kinetic energy of rotation is 1/2 I omega squared. Moment of inertia is I, which is the sum of mass times radius squared for all the sum objects. And there's a few formulas we went over. Kinetic energy of an object rolling without slipping is 1/2 mv squared plus 1/2 I omega squared, where omega is V over r. And when solving problems involving conservation of energy, you need to take into account both the rotational and linear kinetic energy. So let's move on to chapter 11 about rotational dynamics and static equilibrium. So we're going to define a quantity called torque. Torque is the rotational equivalent of force. Torque is radius, well, if I want to get it exactly right, it's radius cross force. But I'm not sure if I have the order right there. But it's radius times force. If you're applying a force at right angles at a radius to a lever arm and a radius r, you will get a torque equal to radius times force. The SI unit is Newton meters, because newtons times meters. The torque increases as the force increases and also as the distance increases. Now, newtons times meters would be joules. But for torque, we always call it Newton meter to differentiate between torque and energy. Because they have the same units, but they're different things. Now, only the tangential component of force causes a torque. So the actual torque equation you get is torque is radius times force times the sine of the angle between them. Because only the component that is perpendicular to the radius creates a torque. This is expressed in the cross product. I just can never remember if it's radius cross force or force cross radius. So like how work is a dot product, torque is a cross product of vectors. I believe it is radius cross force, but I should check it. Just quickly look it up to make sure I'm not getting this wrong. I mean, the difference is a minus sign, so it's not a huge difference, but okay, it's radius cross force. I did remember it. So only the tangential component. So if you apply a force in line with the radius, you get zero torque. If you pull out on a rotating thing, it doesn't rotate it. So torque is the equivalent of force for rotation. So this leads to the more general definition of force. Torque is equal to radius times force times the sine of the angle between them. Yeah, it's radius cross force. You may also hear it referred to as moment. So there's this thing called the moment arm. That's radius times the sine of the angle. That's if you look at the force and you think about the distance. If you extended the line of the force, the distance from the axis the force is applying at, that would be the moment arm. Or you can think about the component of the force perpendicular to the radius times the radius. Those are the two ways to think about it. They give you the same answer. Sometimes it's easier to think about a moment arm. Sometimes it's easier to think about the component perpendicular to the radius. Depends on the situation. Engineers will call torque moment because they're different. They speak a different language. So if a torque causes a counterclockwise angular acceleration, it is positive. If it causes a clockwise angular acceleration, it is negative. So force 1 here, which is causing a counterclockwise rotation, is positive. You can figure this out with the right-hand rule for cross products. Out of the page is positive. I mean, you can curl your fingers in the direction of rotation. You use your right hand, your thumb will point in the direction of the torque, which is out of the page positive. Because this is how you expand this into 3 dimensions. You can also do the first term in the cross product radius times the second term force. Your thumb points in the direction of the cross product. So counterclockwise angular acceleration is positive. Clockwise is negative. So force 1 here is causing a counterclockwise rotation. So it is got a positive torque. Force 2 here is causing a clockwise rotation. So it is a negative torque. If I have a 0.5 meter long wrench, 0.5 meter long wrench, and I apply a force of 12 newtons to it at an angle of 90 degrees, how much torque do I apply? So I'll give you a couple minutes to work that out. So this is fairly straightforward. Force is 12 newtons. The angle is 90 degrees. The radius is 0.5 meters. we want to find torque. Torque is force times radius times sine theta. I should have done radius times force times sine theta, but whatever. So 12 newtons times 0.5 meters times the sine of 90 degrees, which will come out to 6.0 Newton meters. And because this is technically a cross product, it is a vector coming out of the page. That's how you deal with rotation in 3 dimensions. Rotating around an axis, points along the axis, if it's rotating in the directions the finger of your right hand curls, that's where your thumb points in the direction of the rotation. So that's the torque. So here we have a 0.35 meter radius steering wheel and apply a force of 16 newtons to it at 60 degrees from the radial line. As shown, how much torque do I apply? And you can assume this comes out to positive. So again, force is 16 newtons, theta is 60 degrees, the radius is 3.5 meters. We want to find torque. Force times radius times sine theta, 16 newtons times 0.35 meters times the sine of 60 degrees, comes out to 4.84 Newton meters. And it would be positive because this is force 1 in the picture because it's causing a counterclockwise rotation. Now, torque is the equivalent of force for rotation. With a little bit of algebra, we can go from acceleration equals force over mass to alpha equals torque over I. So torque over moment of inertia. We both, because alpha is acceleration over radius. So if we divide both sides by radius, we go from acceleration to, we have alpha equals torque over moment of inertia. Or equivalently, the sum of all torques equals moment of inertia times alpha. And in the last couple of labs, we did a bunch of things with levers where we were dealing with force times distance. Those were all torques. Levers work on balancing torque. So once again, we have analogies between linear and angular momentum. Mass is equivalent, moment of inertia is equivalent to mass, alpha is equivalent to acceleration, torque is equivalent to force. So remember that torque equals moment of inertia times alpha. If I have a disk with a moment of inertia of 15 kilogram meters squared and apply a torque of 30 Newton meters to it, what will its angular acceleration be? Well, this is fairly straightforward. Our moment of inertia is 15 kilogram meters squared. Our torque is 30 Newton meters. Our acceleration is what we're looking for. Torque is moment of inertia times acceleration. So acceleration is torque over moment of inertia. So 30 Newton meters divided by 15 kilogram meters squared gives us 2 radians per second squared. Radians are unitless. If you work through the units, remember that a Newton is a kilogram. So this is 30 kilogram meter per second squared times meters over 15 kilogram meters squared. The kilograms cancel, the meters cancel, and you're left with 2 1 over second squared. Which is what radians per second squared. Because remember, radians are unitless. So that was torque and its relationship to acceleration. Now, much like we had problems with force where things weren't moving, we had translational equilibrium where all the forces canceled out. There's what's known as static equilibrium. That's the more general version of translational equilibrium, where an object is completely at rest. It is neither rotating nor translating. And if you have something in static equilibrium, it has this nice property where the sum of all the forces is 0 and the sum of all the torques is 0. So static for static equilibrium, sum of all the forces in the x direction equals 0. Sum of all the forces in the y direction equals 0. Sum of all the torques equals 0. And one of the nice things about static equilibrium, because the sum of all torques equals 0, you can choose whatever axis you want, which means you can choose your axis or your torque equation to whatever is most convenient. So if the net torque is 0, it doesn't matter what axis we choose rotation to be around. So often it's quite useful to choose the one that makes your calculation easiest. In general, the easiest way to approach this is often to put the axis of rotation where you have unknowns. Because if you have multiple unknowns, you can get rid of one of them by putting it at the axis. So here, for example, I would either put the axis of rotation at F1 here or F2 here. So if I choose this for the axis of rotation, my torque equation won't have, F1 will cancel out of my torque equation. If I choose this one, F2 will cancel out of my torque equation. And then I can get those from my force equations afterwards. But it means I can write a torque equation that only has one unknown in it, so it's easy to solve. Sometimes you'll have like a couple forces at one point and only one force at another that are unknown. You can use that pair of forces as your axis of rotation. It's helpful. Solving these sort of static equilibrium problems is a big enough subject. There's actually an entire class on it for engineers called statics. If you have both horizontal and vertical components, in order to be in equilibrium, an object has to have no net torque and no net force in both the x and y direction. So for this, you have some tension here, you have some mass at the end pulling back. I would set my axis down here because it has both an x component and a y component, and I can make them basically go away by choosing here. And then I have this tension at a lever arm of V and this mg at a lever arm of H. So these, often in these sorts of problems, it's easier to use the moment arm to simplify torque calculations. So the torque, the formulas I would use, I would sum all the forces in the x direction, and you'd have Fx minus tension equals 0. And then do it all for the y directions. You could Fy minus mg equals 0. And then lastly, for torque, the net torque equals 0. We'd use this Vt, this vertical component, times tension, the tension here equals minus the horizontal component times mg equals 0. And you can solve for the various values, the tension and the forces at this point here. So here's an example problem. We have a child of mass m supported on a light plank by his parents who exert the forces shown in the sketch. Force 1 and force 2. Find the forces required to keep the plank in static equilibrium and use the right end of the plank as the axis of rotation. So remember, sum of all forces in the x direction equals 0, sum of all forces in the y direction equals 0, and sum of all torques equals 0. And torque is going to be force times moment arm, generally, is the easiest way to do it if you have vertical and horizontal forces. So let's start by writing out our equations, our equation for torque. So our axis of rotation is here. So clockwise rotations are negative, counterclockwise rotations are positive. So starting with from the left, we have negative, because this is clockwise, minus force 1 times the length of the board, plus mg times the length over 4. That's positive, that's counterclockwise, plus force 2 times 0. So we can solve for force 1. Force 1 times length equals mg times length over 4. Length will cancel. We get force 1 equals mg over 4. Forces in the y direction. We can now do the forces in the y direction, the vertical forces. Forces in the x direction aren't very interesting because there aren't any. That's just 0 equals 0. Not very interesting to write out. Force 1 plus force 2 minus mg all equals 0. So force 2 equals mg minus force 1. So force 2 is mg minus mg over 4. Force 2 is 3 mg over 4. And so those are the forces, force 1 and force 2, around mg. And then we have center mass and balance. So if an extended object is going to be balanced, you end up supporting it through its center of mass. If you work out the equation to balance this via torque, you'll figure out that that point of balance is at the center of mass. I'm going to stop that today. We'll continue this next week. We're not going to have a lab today. We'll have the lab next week. I add a few more slides to this to do a couple more example problems because 11 was a little short because originally I had been rushing through it, but we're going faster than previous. And then we'll start chapter 13. So we should finish off chapter 11 and start chapter 13 on Monday. And then, yeah, we'll continue on from there. Have a nice day. If you want to pick up your tests, they're up here. You all did quite well. Thank you for making grading easy.